this lecture, I want to continue and actually conclude the chapter on sampling and on band-limited signals. In this lecture, we will continue our discussion about the sampling theorem, and we will explain the meaning and application of the sampling theorem. We'll talk about how to recover the original signal from the sampled signal, and then we'll talk about the Nyquist rate, and I will give examples and applications. Last time we showed that when we sample at a frequency omega s, so in the time domain, we're sampling at a frequency, we're sampling with a period t, so sampling every t seconds, let's say if your unit is a second. This means that your frequency is an angular frequency, so this is the sampling frequency is 2 pi by t. This is the angular sampling frequency. Then if you look in the frequency domain at your sampled signal, it's going to be just copies of the originals of the spectrum of the original signal that are just repeated and centered around omega s. So these are shifted copies of the signal that are shifted to be centered around omega s. And then we talked about two important cases. The first case is when there is no aliasing, when omega s is strictly greater than 2 omega 0. So if you're sampling at a frequency greater than twice the largest frequency in the signal, then you don't have aliasing, meaning these copies do not overlap, and this is something very good. Now, if you're sampling with a lower frequency, meaning you're undersampling your signal, meaning your TS is big, right? So you're not sampling fast enough, then you're going to have aliasing because these copies are going to overlap and somehow you lose the shape of the original signal in the spectrum of the sampled signal. So you start seeing here that you don't know what's going on in this part here. Now let us assume that I'm in the good case where there is no aliasing, where I'm sampling at omega s greater than the Nyquist rate, which is 2 omega 0. Now how can I recover from the green spectrum? This is the spectrum of the sampled signal, the discrete signal. How can I recover the original signal? Well, this is easy. All I need is to retrieve one copy. So all I have to do is that to let this sampled signal, xp of t, go through a low-pass filter, and the low-pass filter is just going to pick up these frequencies that I care about. So it's going to pick up one copy of the original signal. So the output of the low-pass filter is going to be a copy of the original signal. Now, maybe I'm not going to care too much of it. It's going to be scaled by 1 over t because of the sum. Because if you remember, you had 2 pi over t in times this sum in the pj omega, but that's not an issue because you can multiply here. You can just scale it by multiplying by a constant, by multiplying the spectrum by a constant. So, and this is really amazing because out of discrete samples, I could recover the original signal by just doing a low-pass filter. So all I have to do is just sample at a frequency larger than twice the maximum frequency of the signal, and then the discrete signal, make it go through a low-pass filter, and then I can recover the whole analog signal. Now this way of recovering the analog signal by making it go through making the sample signal xp of t go through a low-pass filter is called sinc interpolation, and I want to explain a little bit what's going on in the time domain. So you saw what's going on in the frequency domain, but if you want to understand what's going on in the time domain, now again, seeing these things in the frequency domain is interesting, but it's interesting to see what's the equivalent thing in the time domain. So the low-pass filter is given with cutoff frequency omega 0 is given by the following impulse response. So it's sine omega 0 t divided by pi t. Now the recovered signal xr of t, so you're multiplying your sampled signal by h of by the frequency response of the low-pass filter. So that's a multiplication. So in the time domain is going to be a convolution. So this is why the recovered signal is going to be the sampled signal xp convoluted with h of t, right? So which means that an h of t, xp of t is an impulse train, so you're going to get that the recovered signal, meaning the output of the low-pass filter, is going to be the sum over n, xn of t, ht minus n t. So basically, if you replace h by the impulse response of the low-pass filter, you'll see that what you're having, the original signal, is a number of, these, or sampled value time shifted value of sinc function. So we're interpolating these sinc functions. So we're adding infinite number of shifted versions of these sinc functions, and by doing so, we recover the original band-limited signal. To give you an example, so let's suppose we're talking about an audio signal. So typically human beings can hear up to 20,000 hertz, which means that all you have to do is sample an audio signal at twice that frequency. So you have to sample at 40,000 hertz. And this means that you can, so if you sample at 40,000 hertz, you can recover greater than, so omega s. Well, I'm going to call it fs because I want to express it in hertz. So fs should be greater than 40,000 hertz. So, and if you sample that fast, then you guarantee you can recover your song or your interview with not much, actually with no degradation of quality. And this is what MP3, for example, or other standards encode the video. And then to recover, when you want to play the video, play the audio, all you have to do is just pass it through a low-pass filter, and then you can recover the song in a high fidelity quality. So to summarize, if we are given a signal x of t that is band limited, then if I do impulse train sampling, I'm multiplying this signal by an impulse train, so a sum of deltas, right? So this is my signal here, and then I get the signal xp of t, which is going to be these deltas that are modulated, or the amplitude, they pick up the amplitude of the signal at these different times, at the times every t second. So the magnitude of the delta is going to be given by the signal, and the sampled signal is going to be xp of t, and in the frequency domain is going to be just copies of the spectrum of the original signal. And like I said previously, so if omega s, the sampling frequency, is greater than 2 omega 0, omega 0 being the maximum frequency in the signal, then the copies of the original signal will not overlap, and then when I add them, they will not distort the original spectrum, and therefore I can recover one copy by just pushing it through a low-pass filter. And this great result is known as the sampling theorem. I think this is one of the most important theorems or result that you should remember from this class, in addition to convolution probably. So this is super important. You're going to see it all. If you're an engineer, you must know this theorem. And it says that if you sample fast enough, twice the maximum frequency of a signal, then you can recover the signal exactly just from the sample point. You can recover the signal at any time, the whole signal, the whole analog signal, just by sampling it faster than twice the frequency. And this is what I'm saying here, so it's a very important theorem, and sometimes you have to leave a little bit of space between omega s and 2 omega 0 to make sure that you don't have aliasing. So omega s should be strictly greater than omega 0, and there is an example in the book about that. And again, maybe a definition that I mentioned before, so we call 2 omega 0, this is the Nyquist rate. And this is the most important threshold that determine how fast I should sample at. Above this threshold, I can recover the signal. Below this threshold, meaning I'm undersampling, which means that I'm not picking up samples fast enough, so I'm going to be losing some, or getting some distortion on the signal, meaning I cannot recover exactly the signal, and I may recover an alias of the signal that matches the signal at the points, but maybe different. So that would be the Nyquist rate. Now let's do some examples. So here the question is to find the Nyquist rate for the following continuous time signals, and I have 3 options or 3 questions. And again, to find the Nyquist rate, I have to find the maximum frequency of a signal, and the Nyquist rate would be twice that frequency. So here you can see that in the first signal, the largest frequency is, and cosine is 200 pi. So I have to sample at a frequency greater than 400 pi. And the second signal here, it's 30 sine 30t divided by t. So you can see that this is basically this is an LPF. It's missing a pi here, but you can multiply by pi. So it's an LPF with the cutoff frequency 30. So you have to sample at a frequency greater than 60. And in the last example, we're given that this is the following. This is the following spectrum of the signal, and you can see here that the maximum frequency is 60 pi, so you have to sample at a frequency greater than 120 pi. So basically you want to, maybe the importance of this example is that you want to find the maximum frequency on both sides, because again, if you answer 40 pi, then when you shift this guy here with omega s, if it's equal to 80 pi, then you're gonna create some overlap. So this is why you wanna take into consideration the biggest frequency on each side, because these things are gonna be shifted. Now, just a little bit of motivation and engineering. So in general, we like to work with discrete signals, because then we can represent them by bits, and we can process them fast on our computer or on our chips. So they're much easier to process. So typically for band-limited signals, so what we do, we go from continuous to discrete by sampling, and then we process the sample signals. We get the filter. Let's say if it goes through filter y of n, we get the discrete output, and then I can go back to continuous by using sampling and the recovery method that I talked about by using the sampling theorem. So the sampling theorem is a very important component that because most of the signals that we deal with in practice are band-limited signals, or we can make them band-limited by cutting off high frequencies that maybe are not audible or are not noticeable by, if we're talking about video that the eye cannot notice, or even depending on the quality of the video. If you want to compress more, maybe you kind of cut more frequencies off. So you can make the signal low frequency or band limited at the expense of some distortion or some quality, and then it'll be easy to process. Now, some comments about in practice is that the C to D or D to C converters actually mean more processing. So this means that there is some delay. This is why sometimes doing things in analog is faster. Also, to get back the continuous time in MATLAB, you need to determine T and set the f of s, the frequency, the sampling frequency equal to omega s divided by 2 pi. So basically omega s. So the sampling frequency is 1 over T basically. And recall that LPFs, low-pass filters, ideal low-pass filters are impossible to build because they're not causal. So all what I talked about recovering the signal exactly is conditioned on the existence of the ideal low-pass filter, but that does not exist. But again, we can build causal low-pass filters that approximate the ideal ones, and maybe that will introduce some distortion, but still it'll be the output, if the filter is well designed, the output will be acceptable, or the quality of the output will be acceptable. So here I conclude the chapter on sampling. Again, so the main concept is the sampling theorem, which says that if I have a signal that is bandwidth limited, meaning the maximum frequency is omega 0, then if I sample it at twice omega 0, I can recover the signal just from the sample points. From the discrete, I can recover the whole continuous time signal at any time. And this has huge impact on engineering applications.